At how they accomplish those art projects, the amount of engineering that goes into that is intense. And and you have an artist who has a vision, and they're like, I dream up of this big piece of work, and then they go and try and do it on their own, and they can't. They need an engineer. They need the architects. They need the scientists who can help explain to them the math behind how they can get their art to work. Because art is math, and a lot of it is math. And there is an amazing fact. All of that is based on that early principle that you can run multiple different things simultaneously. And so in my career, I started out in IT when I was 21 years old. I was still in college, still didn't know what I wanted to do. Computer science wasn't a recognized degree unless you were in mathematics. So you had to be you had to go into a mathematician degree to get into computer science. That's no longer the case, but that's where it was when I was there. So I was like, I'm not going to be a mathematician. So I never pursued that as my degree. But what I did was I started leaning on all of those scientists and all of those professors that were mathematicians, and I started learning from them. And so early on, I started getting into open source. So when you guys think of Linux, Mac OS, even Windows, they all leverage open source technologies. And open source came out in the 90s. And I was there right in the beginning when none of that was a big deal. Nobody cared. In fact, when you said, oh yeah, I'm using Linux, they were like, okay. And then when you went to a company and said, hey, I want to use Linux in our company, they'd be like, no, that's not known. We don't understand it. We don't get it. Where's the company that supports it? Who can we sue later on if it goes bad? and so it kind of floundered way early on. But open source software was where people started learning, and they started learning quickly. So the idea that we can learn all of this material today came out of these ideas where we said knowledge should be shared, and we should be sharing it at fundamental computer principles, the operating system, that code. If you want to go take Linux and go take the code, you can take it, modify it, do whatever you want to it, and create your own version of Linux. Anyone can do it. In fact, in one of my companies that I worked for, we actually took, the operating system was called FreeBSD, which is it's in the same category as Linux, but we took that, built our own operating system, and used it in one of the earliest Wi-Fi devices that ever existed. Because back in the late 90s, Wi-Fi didn't exist. And when it did exist, it was only 1 megabit per second. So this was in the late 90s, and the company I worked for was actually Maverick. And if any of you have ever been out west, Maverick Country Stores, I was the director over their network and software infrastructure for them for about 9 years, up until about 2007. And early on, we wanted to have Wi-Fi in the source. This was back in 2000, when nobody was thinking about this. Well, we were like, well, how do we do this? Nobody has any software. And so we started looking into open source to figure out how to do that. Now, we ultimately didn't end up going that route. By the time we actually got something figured out, the big providers started selling hardware. So we were like, okay. But we learned. We learned what it would take to build our own things and to build our own solutions. And ultimately, Maverick, in the early 2000s, had the largest implementation of FreeBSD in the Intermountain West. They had over 500 servers running FreeBSD. But we only got there because we were able to demonstrate how we can take this software that nobody knew about and how through our own leveraging we went in and modified it and wrote our own code and started writing our own technologies to drive it. And we ended up building software that was competitive to other commercial software that was solving that same problem. So open source was my learning playground. If you see that this laptop, it's Linux. It's Ubuntu. I'm running Ubuntu on my laptop. Now I run Ubuntu because while I love FreeBSD, I just don't have the time to make it play right and play well with the hardware. So I'm running Linux and I run Ubuntu, and I still look at the kernel code, I still study it, I still enjoy looking at the data structures that make the kernel work. So in the late 1990s, I ended up starting my own internet service provider in Wyoming. So Wyoming had very little on the internet, nobody really understood it, it was all local communities. And so me and a bunch of friends were like, we have a whole lot of technology that would allow us to become an ISP without a lot of money. And so we had the first ISP in the whole state that was running completely on open source. And we were doing things that didn't even exist in commercial hardware. So one of the things on the internet is you all get strained by ISPs throttling, right? You're always, when you say, hey, it's unlimited bandwidth, and then in the small print that says after you get above 10 gigs, we're going to slow you down. Well, there's a piece of technology that runs on the networking equipment that says when you come through it, if you've reached that limit, what we're going to do is we're going to start dropping. We're going to throw away packets. And it just starts throwing them away. And what that forces your home computer to do is resubmit another request. What that ultimately does is slows down the transfer. Now there's different models out there where instead of throwing it away, they just hold it in the memory for a second and then release it. And they keep doing that. So there's different models that do that. But early on, that's the model we used. Was you threw it away and it forced the client to reconnect. That wasn't done even in Cisco hardware at the time. But because I had uncovered a research project at Carnegie Mellon, I took that, played with it myself, started writing code around it, and we implemented our first quality of service solution that no one else had. Because Cisco didn't have it, and most people used Cisco at the time. So that, and of course, as Cisco came out, you got your vendors now doing it, which made doing it yourself impractical over time. But we learned. We learned new ways of doing things. And now, and by that same means, we ended up doing this with Maverick. They have over 300 stores in the Inter-Mountain West. Most of them are in rural areas that have no internet connection. And so we started implementing satellite communications to all the stores. Well, the equipment to be able to transfer data back and forth between the stores and our corporate office was going to be so expensive. And at this time, we were dealing with 9/11. So 9/11 came in, nobody traveled. 2002 came around, and the company made $100,000 that year, that last year. That was it. Now they did better than every other convenience store chain because they were losing, the other ones were losing money. But they only came out with $100,000. So they came to IT and said, do whatever you want. You can do whatever you want, but you can't spend any money. And so we're like, hey, we know a ton of open source software that can help drive all of these things that the company wants to do without us spending any money. And we ultimately, the whole company ultimately ran on open source, except for their IBM mainframe. That was the only thing that wasn't, in fact, we ended up installing open source on it. So even that, we were still using open source on that platform. So here we have open source, which is built by mathematicians, designed by university computer science groups, being trickled out into the people that were still trying to learn it all and trying to catch up with what the universities were doing. And myself, I loved engaging with university projects, and especially at that time. It's a little different now, but at that time, there was some like hardcore new ideas being built at rapid speeds. And so I always wanted to be a part of that, so I engaged in my own coding, in my own development, in my own study. It was always in open source systems. Now, we don't have to do that today. I mean, you don't have to run the Linux to do the same things you can do on Mac OS. You don't have to dig deep, unless you want to. And that's the beauty of computer science, is you can. And you can go as deep as you want to go, as fast as you want to go, and do things that push computing to new limits. This was the first person that I ever idolized in IT. His name is David Korn. He has a sense of humor. This is his favorite picture. David Korn is a PhD mathematician who worked for AT&T. He developed the Korn shell. And I got introduced to him during a project in the late 1990s. He was writing a software called UWin, which allowed you to run Unix software on Windows. Brought this up the other day about that Unix has always ran on Windows. So whenever you think about that, Linux is kind of new, and it's like, ooh, they're finally running Linux on Windows. That's not true. That's not true. It's been done since the beginning. And David Korn was one of the first. And so he wrote what was called UWin. And this is where I come into play. The company I worked for ran their software on Unix. The business side of the house said, we want our product to run on NT, Windows NT. We said, well, it can't run on NT. It's all Unix based. And so I found his project, and we started digging into it in our research and development. And I spent 1 month porting all of our software to Windows NT running on UWin. Well, guess what? I found a bug. I found a bug in David Korn's code. The guy I idolized. I brought it up with my team, the R&D team. I said, how do I go about this? How do I tell a mathematician who wrote the Korn shell that he has a bug? So when I first sent him the very first email, I just did this, hi, my name is blah, I've been using UWin for a little while now, and I think I found a bug in it, and here's how I found it, walked it through. He came back, very short sentence that says, you didn't. I was like, but I did. And here's the bug. And so I started taking screenshots, and I captured all of this information, and I sent it to him again. He goes, well, you're just doing it wrong. And so I said, another email back. And we had these back and forth where I kept sending him more information and was trying to dig out more data into what was going on. And then all of a sudden, I get an email with an attachment. And all it says is, here's a patch. That's it. That was it. And it was that defining moment in my career where I knew what I was doing was what I loved to do, and that I wanted to keep doing this. I was like, here I was working with a mathematician on his code, pointing out a flaw in it, and finally getting him to admit to it. That's a great experience. And it became my little badge of honor. I was like, what's my claim to fame? I found a bug in David Korn's code. Now, David Korn, he went on to go work for Google. And he worked for Google until 2018. And he had a major impact on the underlying architecture and software of Google's platforms. Now he's retired, and now he just gives you a stubborn face and jokes about himself. You know, the thing you want to do in computers is you create groups, you create friends, you have people that are like-minded, who think like you. They want to be part of this community that's building something neat. It's kind of how Google started. Google started because a bunch of people got together and they were like, hey, we wanted to make search easy. But solving the search problem was an intense math problem. So you had a lot of mathematicians involved. In the BSD Unix, which is that variation around, that's in the same category as Linux, they're different enough that they're in that same category, started building a community because its technology was actually really impressive. And they started building a community, and I met this woman, and her name is Drew Levine. And Drew Levine became the director of the FreeBSD Foundation. She became a proponent of open source. And her and I got to work on multiple projects together, including FreeBSD itself. So working for Maverick, where we were now using, we had 500 FreeBSD systems, we became part of those projects. We became contributors. The other one was Samba, and we became contributors. If you don't know what Samba is, Samba allows, it even runs on Mac OS, it is what allows Mac OS, Linux, other non-Microsoft systems to speak to the Microsoft systems. So Samba was an old technology that's now integrated into everything. And so we were active contributors to that. We worked with those projects because Maverick was building their whole infrastructure on these projects. So we got to do a lot of software engineering, a lot of documentation, a lot of development, a lot of testing. And by doing that, we became friends with these people. And Drew was one of those people that had a major impact on me in why communities are important. And she still leads the FreeBSD Foundation to this day. About 5 years ago, well, it's been a little more than that now, a little over 5 years ago, I had the opportunity to work for a company, and they said, we want to build a cloud platform that competes with AWS in a specific vertical. And that vertical was long-term care. So the long-term care facilities, they all need technology, they all have regulations, they all have things that they need, but didn't want to put their data out inside of AWS. So they came out and they said, well, we want to build our own cloud platform. I said, Travis, go figure that out. And before that, I've been doing massive scalable computing for different hosting providers and managed service companies. And so when they came and said this, they're like, do it any way you want. We don't know what this looks like, so go figure this out. We got connected to Marquette University, Milwaukee School of Engineering, and University of Wisconsin at Madison's computer science department. And each one of them had PhD doctors that I met and I ended up working on building a cloud platform that at the time we were even looking at 3 patents. So it was even becoming patent-worthy around the work we were doing, which was around the implementations of algorithms around networking, implementations around algorithms around, for placing VMs. Like, so out on AWS, if you say, I want a VM, do you tell it where in the cloud to put it? You set the region, right? You say US East. You don't know where it's going on their back-end hardware. But AWS, they have to know. Because if you put a VM in there that's doing heavy I/O, and the other person's putting a VM in there with heavy I/O, and they put those right on the same server together, all of a sudden performance is going to go south. So they have to make decisions to say, well, we're going to take your VM, we're going to put it over here. We're going to take the other person's VM, and we're going to put it over on this other server. You don't know about it, but we're going to manage it for you. These were the same algorithms that my team and myself were writing to be able to do this for this cloud platform. And we developed an algorithm, and it was, we coded it as Shaolin. It was referred to as the Shaolin algorithm, which is self-healing and optimization, was what it was short for. So the self-healing and optimization, what it would do is the algorithm would look at all the characteristics of every one of the clusters. We looked at particle swarm optimization algorithms. We looked at the marriage algorithm. We looked at, the other one just slipped out. And we used these algorithms to figure out how we're going to place VMs in our clusters and where on the globe VMs are going to go. So if someone came in from Europe and they said, well, I want a VM, and they went to a web interface in Europe and said, I want a VM in the US, go. Well, we would have to make sure that was routed over to the US infrastructure, being able to be picked up and deployed and programmatically decide where that VM is going to ultimately go. without the user caring because they just want it up. So we have to report all that data back, but at the same time we have to calculate all that. We're going to have to communicate back to the user that it was completely successful, that it is up and running, and that everything about that VM that they wanted is up and stable. The requirements around doing that means you're constantly gathering data. And so the algorithms that you're writing and the data structures that you're designing become very critical. We're doing data science at this point. Things like Python and Pandas together being used to do calculations on data that's coming in hot. So you're getting data from these physical hardware that's saying, is this node healthy? Because if you go to deploy a VM onto some physical hardware that's starting to fail, you have to know that. Which means you also have to have software and systems that's reporting that same level of data. And so we spent years on this product. We got to the point where environments could consist of VMs and containers. And we're really impressed. The architecture was sound, and then that's what Google did. Google created a platform called Kubernetes. And one of the business side of the house came to me and said, hey, could you do a comparison between what we're doing and what Google Kubernetes is doing? So I sat down, did the line-to-line comparison, and I went, crap. And found that Google was doing the same thing. And because they're Google, they're going to succeed. Ultimately, the company from the business side said, well, we're just going to do something. Okay, so, but as a computer scientist, did I lose anything out of that deal? I didn't lose a single thing out of that deal. The amount of knowledge that I had gained from that experience has helped me everywhere I've gone. Because I have spent time designing the underlying software and systems for really complex products, I could now walk into other businesses who were just scraping the surface and knowing exactly the consequences that they're going to deal with when they say, hey, we want to build a cloud platform. I'm like, are you sure? Because here's now the requirements to make this happen. And here's the technical requirements to make it happen. And then I had one company who come in and said, we want to create a system that allows us to deploy a VM just like AWS does. I said, fantastic. You understand what that requirement means. Because when people say that and they say, I want us to build a VM just like you do with AWS, it's like, all right, so what you're asking is that we build AWS, right? Yes. Yes, that's what they're asking. They don't realize it because they're just like, because their context of the world says, AWS has a button I can push, I want a button I can push. Well, all of us in computer science go, what does that button do? When I click that button, am I going through 100 different steps that I have to go through? Is there algorithms involved? Is there inventory systems, change management systems, processes that have to be managed through, security compliance, industry compliance, all pieces that have to be applied when someone says, create me. As computer scientists, you have the ability to explain the underlying system requirements to creating a cloud. You know, when you look at like Amazon, and you've got the button that says, single click buy button. You ever looked at the patent on that? It's the worst patent ever. It's from the business side, worst patent ever. But the actual requirements behind it are far more than just a single push button. And so computer science is figuring out how to make something super simple to a user and make it meaningful and performing all the complexities behind it. This lady, her name's Debbie Pearl, is a close friend of mine at Marquette. She wrote papers for IEEE on networking. She's actually big in security, and she even does security of online robots. So I presented to her the algorithm that was going to do the end placement. And I walked her through this whole design, and I walked her through the algorithm, the data structures, the programming implementation, and it was the second time that I had that experience where I went, I'm doing what I love. I've just been validated by Dr. Deborah Paroli that my work had meaning, and that it was powerful, and that it was functional, and that it was usable. And it was awesome. And that was a great moment. Now, did the company end up using it? No, because Google exists, AWS exists. A lot of times, business side decides we're just going to go that route because it's easier to support. Did I lose anything? I lost nothing. Because now, I walked away from that company and that experience with new relationships, building cool things that I now understand that no matter what other company I go to, at whatever layer they want to talk to that problem to, I can now talk to. They want to talk about the business impact, I can explain the business impact. They want to talk about the technology impact, like what's the flow, what's the data structures involved, what algorithms are involved, I can speak to that. And now I can go to any company because there's a good chance they don't need that level of engineering, and I can speak to it. And I can guide them and instruct them in ways of solving problems that they couldn't before. Why? Because you have the deeper knowledge to help them understand their simpler knowledge. So computer science is never a lost cause. It is always there. It will always be there. It will always, and as you seek it, it will always continue to the more the spiritual side becomes reinforced. And I have found that to be true in my own life. The more I've studied computer science, the more closer the gospel has become. And the more my testimony of it has grown dramatically because of that time. So, Benoit Mandelbrot. Benoit Mandelbrot is a mathematician. I love him because of what he discovered, which is the Mandelbrot set. The Mandelbrot set, in correlation to the Julia set, also has a correlation to something else called the Fibonacci sequence. And for everyone that's into computer science, that Fibonacci sequence, they're like, oh yeah, that's the basic fun of math. The Mandelbrot set, I highly encourage you guys to jump on YouTube and look up the Mandelbrot set Zoom. And they walk you through how the math makes it so you can visualize that Zoom effect. And it can go into, and what appears that it can drill into eternity. It's awesome. The Zoom just goes on forever. And they talk about it as being as the size of the building. So it's like, okay, we've zoomed in enough that it's now the size of the building. And they're like, okay, now it's the size of the city. Now it's the size of the country. And you're still going in. And it's all recursive functions. It's awesome. And so when in the programming language course, I teach recursion. And I teach recursion because this is the stuff that makes it cool. This is when you figure out that you can create a recursive function that can create a Fibonacci sequence on your own, and you can have it go out to eternity, and then you realize that you can create a Mandelbrot set that coincidentally has Fibonacci numbers in it that they didn't know in the beginning. When Mandelbrot figured it out, Fibonacci they weren't aligned. They didn't tie those two together until people started looking at the math on it. Like, holy cow. You can find Fibonacci sequence in the Mandelbrot set. And when I started studying this, it's still over my head. I'm still wrapping my head around it. But I'm going to get to that point where I understand the math on this so well that I can explain why those fractals exist. And I'm still studying that. Now, I've focused more of my time on different data structures and elements that I never really kind of played in this world. So this is new to me. But here I am, I'm at 46 now, and I still want to study more. You still want to study. You want to do this constantly. You want to keep building your knowledge. How many's heard of the Conway's Game of Life? Nice. Conway's Game of Life is an early machine learning game. And it's built, and it was created by John Gordon Conway, who's another mathematician. You're going to see a trend here. Mathematicians make cool things. But we all, math is hard for me. It's not something that comes easily. I have to spend a lot of time on it. But those people that it does come easy, they can do things like create Conway's Game of Life. Now, Conway's Game of Life has an interesting set of rules. So let me step back. Conway's Game of Life is what's considered cellular automata. Cellular automata is you basically have a grid, and you've got cells in each one of them, and each cell has a rule that's applied to it. And you can actually Google this. If you Google Conway's Game of Life, there's actually someone's created a website where you can play this on it, and you can play with the rules. The rules are simple. If the cell has two or less other cells around it, living cells, it will die. It will die because of underpopulation. Now, you're going to find some interesting biases with this Game of Life, because you're going, well, some people, they're introverts. They don't care. You have less than two people, and you're like, yeah, I'm solid. I'm going to be living long because I don't have to deal with people. But so the bias in this one is, if there's less than two or less, they're going to die off. Less than two, they're going to die off. If there's two or three, then they're going to live, and they're going to stay living. But if you have four or more, they're going to die from overpopulation. So it's the play on, if you're lonely, you're going to die out because there's not enough people. And if there's too many people, you're going to die out. So the game goes, when it starts off with a series of cells, and if you hit start, it will start killing cells because they meet the rules, and it will add cells. And you get some very unique visual representations, to the point where they actually can create what looks like a spaceship going across the screen. Because it's killing cells and creating new cells in such a pattern that makes it look like you have little spaceships flying across the screen. And one of them that I did started out as a small little group, and I got it to blow up into this really large shape, and then watched it decrease back to nothing and die. That's cool. Now, the Game of Life, the reality of it is that, it's just the rules that describe this particular game. Clearly, it doesn't match to the reality of life. But what it gives you is the starting of understanding of machine learning, and artificial intelligence. Because here you have a game that's based, that you set your rules, and you watch the game play itself. So when you think of like games that have AIs in them as players, they've done the same thing. They've created a set of rules that says this player is going to be like this while you're competing against them. And as those rules get met, then they'll either die from being shot or they keep getting stronger. Same thing. And as you start understanding this, you start recognizing this exists in all artificial intelligence and all machine learning. That's just the simplest example. The other one, how many of you looked into a camera with like your phone and you went to take a picture and all of a sudden a little yellow box showed up around someone's face? Any of you know how that does that? What's that?
A little bit.
A little bit?
Not any real details.
So there is an algorithm out there. It's called Hars Cascade. Google it. It's awesome. So what it does, it is a facial recognition. It's an object. Let me rephrase this. It's an object recognition algorithm that takes known pictures of faces, and you can do this with trees. You can do this with any object by showing a list of pictures of that object and a list of other pictures that are not that object. When you then run that software, it can then go, oh, I know what a face is. I know what a face looks like. Now, I actually have this. I have this software on my laptop. If you guys ever want to see it like afterwards, I can show it to you and show you how it's trying to find my face. The funniest thing about it, though, is all I have to do is turn my face a little, and it stops recognizing my face. I close my eye, it stops recognizing my eye. But machine learning is all about taking data that is known and taking data that is unknown and applying rules to it. And in Hars Cascade, there's what's called Hars features. And what it does in its calculation, it uses a little white box, and it uses white and black boxes, and it runs through the whole picture, and it scans for pixel density. So it doesn't even do color. It doesn't know about any color at all. It just knows about the density of the pixel. And when you say there's a picture of a face in it, and it scans it, and it goes, okay, I think that looks like a face. Now it does it again, it goes, oh, I think that looks like a face based on what you just showed me. Because we're telling it it's a face. Then you come in and you put in an object that has like no faces in there. And it goes, this is not a face. And then you come in and you scan it, and it runs through those boxes from the Hars features and says, here's what a face doesn't look like. So that when I stand in front of that camera now, it takes all of that learning that the camera company has done. So they've taken all that data, they processed it, loaded it onto the camera, and then they have the running implementation of that algorithm that takes the data from all of that scanning. It goes, all right, the moment you bring that camera up, the function gets called and it says, is that a face? Because we see something that matches all of our learning. This is used everywhere. It is used by Tesla in their autopilot. There is a video out on YouTube, which I shared with Kenny, that he'd be more than happy to share too with you guys, that shows you how Tesla is taking the Hars Cascade and learning about cars around it, learning about the people around it, learning about the road around it. So that as Tesla's autopilot functions, it's saying, this is what a road looks like, this is what a car looks like, this is what a person looks like, and this is what a stop sign looks like, so that it can make smart decisions. There are other algorithms out there. There's neural networks, which is becoming popular, but Hars Cascade is the foundation for all of this. So I highly recommend taking the time to look at that. What time are we at? Right there. We are, and I'm at the end of my slides. So So that is that's how I got into my career. I love teaching this programming class. We're looking at other opportunities for me to teach some other classes. And I hope that I didn't scare you. Like, a little worried there. And I hope that at least gave you some hope in the future of what we can do as computer scientists. Because ultimately, working in IT can be fun. There's a lot of value in every area of it. But if you want to play like the games with math and the games with technology, it is definitely the deeper concepts of computer science, of the artificial intelligence class, of the concepts of programming languages, which teaches you how all that technology is working and why it works. And that I love. That's what I love. So, that's all I have.
We've got a few minutes for we got a few minutes for questions, comments.
I came in late. Can you do your presentation over?
I'll give you the short version.
I got some
I love
questions.
computer science.
I have questions for my AI class. So we talked about rules, right? That's set up. Okay, what are the rules of the vacuum world? That's what we started. Okay, very simple, right? Yeah, and what happens if it's clean? Moves to the next square. If it's dirty, then you sign it. Right. And so very simple. I just want to mention here that as an application developer all my life, I was trying to think of any of my